Picture, if you can, the deepest part of space you have ever imagined. A place so far from any star that the light around you is only a faint scatter of pinpricks. In that quiet, there is a shape you cannot see, but you can feel it in the mathematics. It is the shape of a black hole, a place where everything falls in and nothing comes back out. Light bends around it, time slows near it, matter spirals down into it, forever hidden from the outside sky. Tonight, though, we are not here for the black hole. We are here for its mirror. Somewhere, on the other side of the equations, sits a stranger idea, a place where nothing can enter and everything comes out, a fountain instead of a drain, a cosmic exhale instead of an endless swallow. Physicists have a quiet name for this idea. They call it a white hole. And whether such a thing exists anywhere in the real universe is one of the softest, strangest open questions in all of astronomy. Imagine standing in the dark near one. If such a thing could be safely imagined, you would see light pouring outward. You would see matter blooming into space like slow petals. And no matter how hard you tried, you could not fall in. The surface would push you gently away, the way a black hole would pull you gently down. It is a shape that looks familiar and impossible at the same time. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Now, back to that strange bright mirror. The reason white holes appear at all is that the equations describing black holes do not care very much about the direction of time. Run the math forward, and you get a black hole gathering matter in. Run the same math backward, and you get something that pushes matter out. Both are permitted. Both are, in the language of pure geometry, allowed. But permission is not the same as existence, and that gap between what the math allows and what the universe actually builds is where our mystery lives. Some researchers wonder if white holes are simply a mathematical shadow, a ghost inside the equations, a shape that can be drawn on paper but never assembled by nature. Others take the idea more seriously. They point out that we have found black holes. We have taken their pictures. We have listened to the ripples they make when they collide. If the same equations describe both, why should only one side of the mirror be real? There are hints, faint and unproven, that a white hole might not be as impossible as it first seems. Some theories quietly suggest that the Big Bang itself, that ancient outpouring of light and matter at the start of everything, might have been the mouth of one. A single, enormous fountain pouring out the contents of another place, another time, another universe. This is only an idea. It is not proven. It may never be. But it is a thought worth holding as you drift. Other physicists prefer a gentler picture. In their view, a white hole is not a beginning at all, but an ending. They imagine an ancient black hole, after unthinkable stretches of time, quietly turning inside out. What went in slowly finds its way back out again, over spans so long that our sun and its planets are only a small breath within them. This idea comes from attempts to blend gravity with the smallest rules of the quantum world. It is beautiful. It is also unconfirmed. And then there are those who suspect white holes are forbidden after all, not by the equations themselves, but by something deeper. By the way heat spreads, by the way order slips into disorder, by the direction the universe seems to prefer for its own story. In their view, a white hole would be a candle unburning, a shattered cup gathering itself back together. Possible on paper, impossible in practice. Tonight, over these next few hours, we will sit with this question. We will look at the equations that first suggested white holes. We will imagine the strange surface that surrounds them. We will visit the theories that place them at the beginning of time, and the theories that place them at the end. We will not solve the mystery, no one has, but we will walk around it slowly from many quiet angles and let it soften into something wonderful to fall asleep beside. For now, breathe out. The universe is very large and the mirror is still waiting. Let us begin with the simplest possible picture. A black hole is a place in space where gravity has grown so strong that nothing which falls in can climb back out. Not light, not gas, not even the smallest whisper of a signal. Everything moves one way, inward, and the door shuts behind it forever. Now flip that picture in your mind. Imagine a place where nothing can fall in and everything must move outward. A door that only opens in one direction, but the opposite direction. Matter and light pour out. No spoon, no probe, no beam of any kind can approach it. That, in the simplest terms, is what physicists call a white hole. The name is not poetic. It is just the mirror of black. If a black hole swallows, a white hole would spill. If a black hole hides its inside from us, a white hole would hide its outside from itself. The two ideas are twins, born from the same equations, separated only by the direction of time. No one has ever seen a white hole. No telescope has confirmed one. The idea lives, for now, entirely inside mathematics and the quiet imaginations of theorists. That is important to hold on to. When we speak of a white hole tonight, we are speaking of a possibility, not a certainty. The universe may contain them. The universe may forbid them. Both answers are still on the table. If a white hole did exist, what would it look like? The honest answer is that we are not sure because the object has never been observed, but the equations offer a rough sketch. From the outside, at a distance, a white hole might resemble a black hole in one important way. It would carry a boundary around it, a kind of invisible edge. For a black hole, that edge is the point of no return going in. For a white hole, it would be the point of no return going the other way. You could not cross it inward. No matter how hard you tried, space itself would push you back. Beyond that boundary, a white hole would shine, or rather, it would erupt. Matter and radiation would emerge from it, streaming outward into the surrounding space. Some models suggest a brief, bright flare, brilliant and short-lived. Other models suggest something quieter, a slow leak of particles over long stretches of time. Which of these is closer to the truth? If either is, remains an open question. The size of a theoretical white hole is not fixed. In principle, one could be tiny, no larger than an atom, releasing a small puff of energy. Another could be enormous, holding the mass of a star, or even a galaxy inside it. Some speculative ideas even stretch the picture further, wondering whether an entire universe might sit on the other side. For scale, imagine a black hole roughly the size of our sun, compressed into a ball only a few kilometers across, small enough to fit inside a modest city. A white hole with the same mass would fit into the same small volume, but instead of pulling the city inward, it would be pushing everything away. The age of a white hole is another puzzle. Many models suggest they would be short-lived, existing for only a flicker of cosmic time before collapsing or destabilizing. Others hint that a white hole could persist for billions of years, quietly leaking material into space. A few of the boldest proposals suggest that the Big Bang itself, the beginning of everything we can see, might have been the outward burst of one enormous white hole. We will sit with that idea in more depth later. For tonight, hold it lightly. Composition is the strangest part. A white hole would not be made of anything in the ordinary sense. It would not have a surface you could stand on, or a core you could examine. It would be a region of curved space-time, a shape in the fabric of reality itself, defined by how it bends the paths of everything nearby. The matter emerging from it could be anything: hydrogen, helium, high-energy photons, particles we have not yet named. The equations do not specify. They only say that whatever comes out, and cannot go back. So the fundamental picture is this: a white hole, if it exists, is a region of space that only expels. It cannot be entered. Its edge is a one-way barrier, its interior unreachable by anything outside it. Its mass could be small or vast. Its lifetime could be brief or long. Its contents could be almost anything. And whether nature actually builds such objects or only permits them on paper is a question we still cannot answer. The story of the white hole does not begin with a telescope or a photograph. It begins with pencil marks on paper, in a quiet study more than 100 years ago. A physicist named Albert Einstein had just given the world a new way of understanding gravity. His equations describe space and time as a single flexible fabric, one that could bend and stretch around anything with mass. And within those equations, hidden like a seed inside a fruit, was a strange possibility that nobody quite knew what to do with. Not long after Einstein published his work, a German soldier, an astronomer named Karl Schwarzschild, sat in a field hospital during the First World War and solved one specific version of these equations. He wanted to know what the gravity around a single perfectly round mass would look like. His answer was elegant. It described the curvature of space near a star, a planet, a small dense object. But the answer also contained something odd. If the mass was compressed into a small enough space, the geometry became extreme. A boundary appeared. Inside that boundary, the math suggested nothing could escape. This was the seed of the black hole idea, though nobody called it that yet. Here is the quiet twist. Schwarzschild's solution did not only describe a place from which nothing could escape, it also described mathematically a place into which nothing could enter. The same equations, read in a different direction, allowed for a mirror image, a region where matter and light could only flow outward. This second region was not added on purpose. It was simply there, sitting inside the mathematics, waiting to be noticed. For a long time, it was not noticed. The idea sat quietly in the papers of theorists for decades. Only in the middle of the 20th century did physicists begin to take the full shape of Schwarzschild's solution seriously. Two mathematicians, Martin Kruskal and George Chequeras, working separately, redrew the geometry in a clearer way. Their picture showed the whole extended landscape that the equations described. On one side sat a black hole. On the other side, connected by a strange narrow throat, sat this other region, a time-reversed twin, what we now call a white hole. The reason it appears in the math has to do with a simple symmetry. The equations of general relativity do not care which direction time flows. If you take any valid solution and run it backward, you get another valid solution. A ball falling into a well becomes a ball rising out of one. A star collapsing into a black hole becomes something ejecting matter outward, forever. The math treats both directions as equally allowed. It does not know which one nature actually chooses. This is the puzzle that has never fully gone away. The equations grant permission. But permission is not the same as existence. A theorist named John Wheeler, who helped popularize the term black hole in the 1960s, was among the first to sit with this strangeness openly. Others followed. Some thought the white hole was just a mathematical ghost, a shadow cast by the symmetry of the equations, with no real counterpart in the sky. Others wondered if such objects might truly exist, waiting somewhere dim and undiscovered. There was no experiment that could settle it. There still is not. The birth of the idea was not observational. It was not a light in the sky that demanded explanation. It was a consequence of taking the equations at their word. If you trust the math, the white hole is already there, folded into the same solution that gives us black holes. You cannot remove one without removing the other. Or so the geometry seems to say, yet nature may have rules that the equations alone do not capture. Entropy, the tendency of orderly things to become disordered, seems to flow in only one direction. Broken cups do not reassemble themselves. Smoke does not gather back into a candle. If white holes exist, they appear to run against this current, at least in some sense. Whether that means they cannot exist, or simply that they exist under conditions we have not yet imagined, remains an open question. So the origin of the white hole is not a place or a moment. It is a line of reasoning. It is what happens when you take Einstein's equations and Schwarzschild's solution and Kruskal's diagram and follow them where they lead without flinching. The path arrives at a fountain instead of a drain. Whether that fountain is only a shape on paper or something that has ever poured its light into the real universe is a question that has been waiting patiently for more than a century for an answer. Picture, if you will, a garden fountain in a quiet courtyard at dusk. Water rises from somewhere hidden and spills outward in a soft, endless cascade. Nothing you drop into it can sink down to its source. The water only ever moves in one direction, upward and outward, away from a center you cannot reach. This is the gentle shape of a white hole, at least in the way the equations describe it. Not a place exactly, but a direction, a fountain instead of a drain. Now, the strange part. A black hole and a white hole, in the theory, are made of the same ingredient. That ingredient is not iron or hydrogen or any element you could hold in your hand. It is geometry, curved space-time itself. Both objects are, at heart, just shapes in the fabric of the universe, sculpted by an enormous concentration of energy. The difference between them lies not in what they are built from, but in which way time seems to flow through them. Still, if a white hole ever did erupt somewhere in the cosmos, the matter it spilled out would have to be made of something. And here the theory gets softer, more open. The material would likely be a hot plasma, a glowing soup of protons, neutrons, and electrons, so densely packed that atoms as we know them could not yet exist. As the plasma expanded outward, it would cool, nuclei would form, then simple atoms. Hydrogen first, and helium in a slow settling that mirrors what the young universe itself did in its early minutes. That mirror is not accidental. It is one of the reasons some researchers have wondered whether the Big Bang was itself something like a white hole, pouring out the raw stuff of everything. The idea remains contested. Others argue the two events only look similar on the surface, and that the Big Bang has no true center and no clear boundary, while a white hole would. The question of whether the beginning of the universe and a hypothetical white hole share a family resemblance is still open. What we can say is that every atom in your body has already been through more transformations than a white hole would ever add. The iron in the hemoglobin carrying oxygen through your blood was forged in the fusion cores of dying stars, then flung out in the slow bright glow of a supernova. The calcium in your bones came from the same kind of stellar furnace. The carbon in every cell was cooked in the belly of a red giant that lived and died long before the sun was born. You are, in a very literal sense, made of star ash. The oceans, too, carry a story that reaches beyond the earth. Some of the water on our world may have arrived here on icy comets and dust-covered asteroids drifting in from the outer solar system when the planets were still young and hot. Other portions may have been baked into the rocks of the early Earth from the beginning. The exact balance between these sources is still being worked out. What is clear is that water, that simple pairing of hydrogen and oxygen, is a traveler. It moves between stars, moons, comets, and worlds. If a white hole ever released matter, the hydrogen and helium spilling out would join this same long story. It would drift into clouds. Gravity would gather it. New stars would ignite. Heavier elements would slowly cook in their cores. And billions of years later, some of that material might find itself inside a rocky planet, or the shell of a sea creature, or the leaf of a tree. Nothing in the cosmos is ever wasted. Every atom is loaned, then returned, then loaned again. The gentle irony is this: a white hole, if it exists, would be a source, a place where new matter arrives in the universe from somewhere else, or from some other time, or perhaps from nowhere our physics can name. And yet the matter it produced would immediately fold into the same ancient recycling that already fills the sky. The plasma would cool, the atoms would clump, the stars would form. The endless, slow shuffle of cosmic chemistry would continue as it always has. Whether that fountain actually flows anywhere, in any corner of the observable universe, is a question no one has yet answered. The equations allow it. The stars do not obviously show it. The material, if it ever came, would slip quietly into the same rivers of hydrogen and dust that have carried the cosmos through its long, patient life. And so we sit with the image of a fountain in the dark, wondering, without needing to know, whether any such fountain has ever truly poured. Think of a river. Water flows downhill, gathering speed, pooling in the low places, warming as it tumbles over stones. Now, try very gently to picture that same river running the other way. Not just backward in space, but backward in every small thing that happens along the way. Ripples smoothing themselves, heat drawing back into the rocks, every scattered droplet returning to the stream. That strange reversed river is close to what physicists mean when they talk about the arrow of time flipping. And it is the force, if we can call it that, which shapes a white hole in the equations. A black hole is sculpted by gravity. Matter falls in, pressure builds, heat rises as gas grinds against itself in the swirling disk outside. Magnetic fields braid and snap, launching thin jets from the poles. Tidal forces stretch anything that comes too close, pulling the near side harder than the far side, drawing objects into long, thin threads. A white hole, in theory, is sculpted by all of these same forces, but every one of them runs the opposite way. Instead of gas spiraling inward and heating up, gas would spiral outward and cool. Instead of matter being pulled in by gravity, matter would be pushed out along the same paths, arriving from a place no telescope can see. Instead of magnetic fields winding tighter and tighter, they would unwind, releasing energy they seemed to have stored from nowhere. Instead of tidal forces crushing objects together, they would gently separate them, easing them apart as they drifted away into calm space. Nothing in the equations of general relativity forbids this. That is the quiet surprise at the heart of the theory. The math does not care which direction time runs. If you filmed a collapse into a black hole and played the reel backward, the reversed film would still obey Einstein's rules. It would show a white hole, The trouble is that the rest of physics does seem to care. Heat spreads out. Cups shatter but do not unshatter. Smoke drifts from a candle and does not return to it. This one-way drift is called the second law of thermodynamics, and it points a steady finger in one direction. We call that direction the arrow of time. A white hole would appear to defy that arrow. Matter and light would leave its surface in patterns that grow more ordered as they travel, at least for a moment, as though the universe outside were quietly running in reverse near this one strange object. Some physicists find this so troubling that they doubt white holes could ever form. Others point out that the arrow of time is a statistical thing, not an absolute law. In a universe of countless particles, unusual pockets might exist where the normal drift briefly reverses. So which view is right? That is one of the open questions this episode keeps returning to. One camp holds that thermodynamics is the deeper truth, and that anything violating it, even locally, cannot be real. Another camp holds that general relativity is the deeper truth, and that if its equations allow white holes, then something in the universe may allow them too, however rare or short-lived. The forces at work inside a theoretical white hole would be almost dreamlike in their gentleness. Imagine an object where gravity, at least in one strange sense, pushes rather than pulls, not by producing a new kind of repulsion, but by making the region inside impossible to enter. Any path you tried to trace inward would run out of future. Time itself would seem to end before you arrived. You would be turned back, not by a wall, but by the shape of the moments ahead. From the outside, the effect might look like a soft glow, radiation streaming outward, a slow rain of particles emerging from a point where nothing had been before. Some models suggest a brief flash, over almost as soon as it began. Others suggest a longer eruption, spread across ages. The equations do not settle this. Different assumptions produce different pictures. What we can say is that every force we normally associate with a black hole would still be present around a white hole, only reversed in its role. Gravity would still curve the space nearby. Magnetic fields could still exist in the surrounding matter. Radiation could still travel outward, carrying information from something we can barely describe. The difference is direction. The difference is which way the story runs. And that is why, when physicists talk about white holes, they often end up talking about time itself. Not just the ticking of clocks, but the deep question of why the universe seems to remember its past and not its future. A white hole, if it exists, would be a place where that memory gets confused. Think about how much stuff moves in the universe each second. Rain falls on a summer field. Rivers empty into oceans. Coffee cools in a cup on a kitchen table. Iron rusts on the side of an old ship. In every corner, from the smallest bacterium to the widest spiral galaxy, things drift the same way. They spread out. They cool down. They mix together until the mixing cannot go any further. Physicists call this the arrow of time, and it points in one direction only. A white hole would be a place where that arrow points the other way. Not a little bit, not sometimes, always, everywhere inside it. And this is why the universe seems, in some quiet and stubborn way, to forbid them. To feel the scale of this problem, picture a single drop of ink falling into a glass of water. In a few seconds, the ink blooms into a soft blue cloud. Given a minute, it spreads through the whole glass. Wait an hour, and the water is a pale, even blue. Now, try to imagine that same glass gathering all the ink back into a single sharp drop, all on its own, with no one stirring it. You could sit in front of that glass for the entire lifetime of the sun and never see it happen. You could sit there for the age of the universe, 13.8 billion years, and still see nothing. The odds against it are so vast that our minds have no shelf to put them on. That is a single glass. A white hole would be an entire cosmic region doing the same trick, at the scale of a star, or a galaxy, or something even larger. Consider the mass involved. A modest black hole has the weight of perhaps 10 suns squeezed into a ball the size of a small city. A white hole of the same class would have to spit that same mass outward in a burst that unwinds every process that ever created it, every photon that fell in, over the entire life of the parent object, would need to come back out in the reverse order it arrived. Every atom would need to find the exact path it once took, only running backward with perfect timing. The precision required is so extreme that if you missed by a single grain of sand out of the whole ocean of possible states, the whole event would fall apart before it began. Try shrinking the numbers to feel them. If you turned every atom in a thimble of water into a tiny switch and asked all those switches to flip in the correct order, at the correct instant, you would already be facing odds larger than the number of stars in every galaxy we can see. A white hole would be that thimble scaled up to the size of the sun, then scaled up again to the size of the sun's shadow across the whole solar system. Then again, and there is the question of age. Our universe has been running for about 13.8 billion years. In that span, everything we watch has cooled. Stars burn hot, and then fade, nebulae glow, and then thin out into the dark. Even black holes, in the very slow leak of Hawking radiation, are thought to give up their mass. Over spans so long the numbers stop meaning much. Sometimes 10 to the 100th power of years, A1, followed by 100 zeros. A white hole would be a small, sudden argument against all of that. A brief, bright refusal. Some researchers wonder whether this apparent forbidding is a true law of nature, or only a matter of how likely something is. The equations of general relativity, the math that describes gravity and space-time, do not actually rule white holes out. They allow them. What seems to rule them out is statistics, the sheer improbability of matter organizing itself into an outward-only fountain. Other researchers push back and note that improbable is not the same as impossible. Rare events, given a large enough universe and a long enough clock, can still happen once, maybe twice. So the scale of the mystery has two faces. On one face, the numbers against a white hole are so enormous they feel like a locked door. On the other, the door is not truly locked. It is only very, very heavy. And somewhere in the deep, quiet distance between those two faces sits the open question we have been circling. If the door is only heavy and not locked, then somewhere, perhaps at the edge of what we can see, perhaps at the very beginning of everything, something may have pushed through it. We do not know. We may never know. For tonight, we can simply sit with the weight of that door. Imagine floating in a place that no telescope has ever confirmed, a place that lives only in the pages of equations and the quiet imagination of physicists. You are hovering in empty space, and before you is something that should not, by every rule of common sense, be there. It is not a star. It is not a planet. It is not even a black hole, though at first glance it might seem like one. It is the theoretical outer skin of a white hole, and around it there is said to stretch a strange geometric structure that mathematicians call a bridge. The bridge has a long name in the older textbooks. It is sometimes called an Einstein-Rosen bridge, after the two men who first sketched its shape on paper. In simpler words, it is a tunnel drawn by the equations of general relativity, a narrow throat of curved space that connects a black hole on one side to its time-reversed twin, the white hole, on the other. If you could see it, and this is a big if, it would not look like a solid pipe. It would look like a slow warping of the darkness itself, a pucker in the fabric of the sky. Picture the surface of the white hole first. It has no crust. It has no soil here. Has no hard shell you could set your boot upon. What it has, according to the mathematics, is a boundary of light. This boundary is the mirror image of a black hole's event horizon. From a black hole, nothing can escape. From this surface, in theory, nothing can enter. Matter and light stream outward from it, always outward, and the outside universe is forbidden from crossing back in. If you tried to paint it, you might reach for the color of a sunrise seen through frosted glass. The outer skin would shimmer with a soft, pale radiance, because whatever spills out of the white hole would glow as it emerged, warmed by the violent conditions of its origin. Some models suggest a halo of hot gas, feathered outward like the petals of a flower opening in slow motion. Other models suggest something quieter, a smooth glow that fades into the black of space, with no clear edge at all. The truth is that no one has ever seen such a surface, and the pictures we draw are only guesses dressed in the clothes of equations. Now step back and try to take in the bridge itself on a diagram drawn by physicists. The bridge appears as a narrow waist between two flared mouths, a shape a little like an hourglass laid on its side. One mouth is the black hole, greedy and inward pulling. The other mouth is the white hole, generous and outward pushing. The waist between them is where space is stretched thinnest, where the geometry of the universe folds in on itself and comes out the other side. If you could stand at that waist, you would not feel a flaw. You would feel a slow, gentle pull in two directions at once, as if the space around you did not know which way to lean. Whether this bridge is real, or only a shape that lives in the mathematics, is one of the oldest open questions in this field. One view holds that the bridge is a real feature of the universe, and that somewhere out in the dark, a black hole is quietly linked to a white hole through a hidden throat of space. Another view held by many working physicists today is that the bridge is a mathematical ghost. In this view, the equations allow the shape to be drawn, but the physical universe never actually builds it. The bridge, they say, would pinch itself shut faster than anything could pass through, closing like a mouth that changed its mind. There is a third possibility, quieter than the others. Some researchers wonder whether the bridge exists for only the briefest flicker of time before it collapses. If that is true, the surface of a white hole would be less a place than a moment, a fleeting shimmer where the geometry briefly opened and then sealed away again. You could not stand on it. You could barely see it. It would be there and gone before a photon had time to complete its arc. For tonight, let the picture stay soft in your mind. A pale, glowing skin, a narrow throat of curved space, two mouths, facing away from each other across a bridge that may or may not be real. The equations permit it. The universe has not confirmed it, and the question of whether such a surface truly exists, somewhere far beyond our seeing, remains open. Let us drift downward now, past the edge, past the bright rim where light itself refuses to enter. In an ordinary black hole, we imagine falling in. In the mirror version, we cannot fall in at all. The white hole, if it exists, is a place matter comes out of, and only out of. Nothing from the outside can move toward its center. This is one of the strangest features in all of theoretical physics, and it is worth sitting with in the quiet dark. Think of a river flowing steadily out of a cave mouth. You can watch the water pour out. You can feel it push against your legs, but if you try to swim upstream, the current grows and grows the closer you get, until no effort would be enough. That is the gentle picture. The real geometry is stranger. It is not that the water is too strong, it is that the direction toward the interior simply is not available to you. Space and time, near a white hole, tilt in such a way that inward is not a place you can go inside. An ordinary black hole, once past the edge, every path leads toward the center. The geometry tips, and the future itself points inward. In a white hole, that same tipping happens in reverse. The future points outward. For any object near the mouth, tomorrow lies farther away from the center than today. You could not turn around any more than you could walk into yesterday. The mystery deepens when you ask what this means for whatever sits inside. We do not know what fills the interior of such an object, or whether the word interior even makes sense. Some physicists picture a hidden core of matter, waiting, releasing itself outward over some span of time. Others suggest the inside is not a place at all in the ordinary sense, but a region of space-time that only makes sense when read backward, like a film run in reverse. Still others wonder if the interior is simply the other end of a bridge, connected to somewhere else entirely. The equations allow all of these readings, and the equations alone cannot tell us which, if any, matches reality. There is another puzzle folded into this. If matter cannot be approached, then matter cannot be studied up close. A probe cannot orbit. A telescope cannot peer inside. Even a stray photon drifting near the mouth would be swept outward before it could carry information in. Whatever a white hole hides, it hides perfectly, not by darkness, but by the shape of time itself. Some researchers find this beautiful, others find it troubling, because a thing that cannot be probed sits at the edge of what physics can even call real. There are competing views on what this unreachability implies. One view treats the white hole interior as a genuine physical region, filled with matter that will one day emerge. Another view treats the interior as a mathematical artifact, a shape that appears in the equations, but that nature never actually builds. In this second reading, the equations describe a possible geometry, the way a blueprint describes a possible house. Not every blueprint gets built. Whether the universe ever builds this particular one remains an open question. The strangeness grows when we imagine the moment of emergence. If matter is streaming outward from a white hole, where did that matter come from? It could not have fallen in. Its history, followed backward in time, does not lead to a collapsing star or an infalling cloud. In the classical picture, the matter simply exists, having always been on its way out. Some theorists find this idea uncomfortable, since it seems to require a kind of initial condition that has no earlier cause. Others point out that our own universe, at its earliest moment, seems to require something similar, and that this resemblance may be a clue rather than a flaw. Down at the deepest layer, the puzzle becomes almost tender. A white hole, if it exists, is a region where the ordinary rules of approach and retreat are gently reversed. You cannot visit it. You cannot send anything to it. You can only stand at a respectful distance and watch what pours forth, if anything pours forth at all. It is a place defined more by its refusal than by its presence. And so, the depths of the white hole remain a question, rather than a picture. We can write down the geometry. We can trace the tilting of light cones near its mouth, but whether any real object in the sky matches this description, and what would be found inside if we could somehow look, are things nobody yet knows. The interior stays quiet, sealed off by time itself, waiting for a physics we do not yet possess. If a white hole ever did erupt somewhere in the sky, it would not look like a steady lamp or a patient star. It would pulse. It would flare. It would arrive, in the imagination of the equations, as a sudden brightening in an empty patch of space, a fountain of light and matter appearing where nothing had been a moment before, and then, perhaps, it would fade. This is the strange rhythm the theory suggests. Not a slow burn, but a brief and violent glow. To picture it, imagine a quiet field of stars, deep and calm, the kind of dark you might see from a mountain far from any city. Now, imagine a single point in that field suddenly swelling with light. Not a supernova, which unfolds over days and weeks with a known shape, something stranger. A burst that seems to come from nowhere, made of gas and radiation that no earlier object produced. The theory says this eruption would not be fed from outside. It would arrive from within the object itself, from a region no telescope can look into. The rhythm of such a glow is one of the deepest puzzles. A star pulses because gravity and pressure trade places over long, patient cycles. A pulsar spins and sends out beams like a lighthouse. A black hole flickers as matter falls in and heats the disk around it. But a white hole, in the equations, does not seem to follow any of these familiar beats. It would open, spill, and close. Some models suggest the whole event might last only an instant. Other models suggest a longer, softer glow that fades over years. No one knows which picture, if any, matches reality. One idea comes from a branch of physics called loop quantum gravity, which tries to blend gravity with the rules of the very small. In some versions of this theory, a black hole slowly transforms into a white hole across an enormous stretch of time. From the inside, the change might feel quick. From the outside, it might take longer than the current age of the universe. When the transformation finishes, the object would release everything it once swallowed in a brief flash. A tiny, primordial black hole, formed in the earliest moments after the Big Bang, might be finishing that cycle right now, somewhere in the sky, glowing for a fraction of a second before going quiet again. A competing view says this cannot be the full picture. Other researchers argue that a white hole, if it formed at all, would be too fragile to hold its shape. It might collapse almost immediately under its own strange geometry, snapping shut before any real glow could reach us. In that case, the eruption would be even shorter, more like a stutter than a shine. The rhythm would be closer to a single heartbeat that never repeats. There is also a quieter possibility, and it is one worth sitting with. A white hole might not glow the way we expect at all. The light it releases could be stretched by the odd curvature of space around it, softened into a low hum of radiation that blends into the background of the cosmos. If that were true, we might already be bathed in the fading echoes of ancient eruptions and simply not know how to recognize them. The rhythm would be there, hidden inside a signal we treat as noise. Some astronomers have wondered whether certain brief flashes seen in the sky, short bursts of gamma rays that appear and vanish in seconds, could be the whisper of such an event. The evidence is far from settled. Most of these bursts have simpler explanations, tied to collapsing stars or colliding dense objects, but a small handful remain unexplained, and the door has not been closed on stranger origins. The question stays open. What draws the mind on a night like this is the way the theory suggests a cycle we cannot quite trace, a rhythm that might play out over seconds or over ages longer than we can imagine. A pulse that begins hidden inside a region no signal can reach and ends in a glow that may or may not have ever crossed our sky. The universe is full of cycles we understand. The turning of galaxies, the breathing of stars, the slow tides of gas between them. This one if it exists, would sit outside all of them. It would be a rhythm without a repeat, or perhaps a repeat we have not lived long enough to notice. For now, the glow remains theoretical. The equations allow it. The sky has not confirmed it. And the question of what such an eruption would truly look like, if it ever came, waits in the quiet. If a white hole is a fountain of matter and light, gushing outward from a point that nothing can enter, then it is worth pausing to consider a strange neighbor to this idea. Something in our own past looks a little like that description. The universe itself, in its earliest moment, poured outward from a single hot, dense state. Space grew. Matter and light streamed away from that beginning, and nothing we know of, no signal, no probe, no thought, can travel back to touch it. Some physicists have wondered, quietly and carefully, whether the Big Bang might have been the mouth of a white hole. The idea is not new, and it is not fringe, though it remains far from proven. The equations that allow white holes on paper describe a place where matter emerges from a boundary that cannot be crossed inward. The Big Bang, viewed on the largest scale, shares that basic shape. Everything we see came out of it. Nothing goes back into it. Time flows away from it in every direction. If you had never heard the phrase Big Bang before, and someone described a white hole to you, you might notice the resemblance. One version of this idea suggests that our entire universe sits on the outward side of a white hole that formed in some larger, older cosmos. In that picture, a black hole in a parent universe could funnel matter through some hidden passage, and on the far side, that matter would burst into a new space and become the seed of everything. The Big Bang in this view would not be a beginning at all. It would be an arrival. What we call the origin would simply be the doorway we came through. It is a beautiful thought, and it must be treated with care. The mathematics that hints at such passages, the bridges buried inside the geometry of black holes, does not by itself prove that anything travels through them. Most physicists suspect these bridges collapse the moment matter tries to cross. The equations permit the shape. The physics may forbid the trip. So the picture of our universe as the far side of some ancient black hole remains a possibility, not a discovery. There is a competing view, and it is worth sitting with. In the standard model of cosmology, the Big Bang is not an explosion in space, but an expansion of space itself. There was no outside, no mouth, no boundary you could point to and call the source. Space simply began to grow everywhere at once. In this view, comparing the Big Bang to a white hole is a poetic overlap, not a physical one. The shapes look similar because both involve matter and light streaming outward, but a white hole has a location. The Big Bang in the standard picture does not. The two ideas do not fit together easily. A white hole, as general relativity describes it, sits somewhere. You could in principle orbit it, or watch it from a distance. The early universe had no distance to be watched from. Every point was part of the event. So even sympathetic physicists, who like the white hole comparison, admit that the fit is imperfect. The Big Bang may resemble a white hole in mood and in direction, but not in geography. Still, the resemblance keeps returning in the quiet corners of theoretical physics. Some models of loop quantum gravity, an attempt to describe space and time at the smallest scales, suggest that the universe may bounce. In such models, an older cosmos collapses, reaches a limit, and then rebounds outward. The rebound, seen from the new side, could carry the flavor of a white hole event. The matter of the old universe would pour into the new one, unable to return. Whether this is what actually happened, no one knows. The bounce models remain one option among many, and the evidence to choose between them is not yet in our hands. there is also the puzzle of where all the matter came from. A white hole, in theory, spills out whatever fell into some paired black hole long ago. If the Big Bang was such a fountain, then the atoms in your body, the light in distant galaxies, the dust of every planet, may all be the exhaled breath of some vanished older cosmos. It is a strange lineage to consider as you lie in the dark. It may not be true. It may be only a shape the equations happen to allow, but the question sits there, patient and open, waiting for evidence that has not yet arrived. For now, the neighbor of the white hole idea is the beginning of everything itself, standing quietly beside it, resembling it in ways we cannot fully explain. Every object in the sky has a story of origin. Stars condense from cold clouds of gas that grow heavy under their own weight. Planets gather from the leftover dust of newborn suns. Even black holes have a clear birth certificate. They form when a massive star runs out of fuel and its core collapses inward, folding itself into a point of impossible density. We can watch this happen. We have seen the flash of a supernova, and later the quiet dark object left behind. But when we ask where a white hole would come from, the sky offers no easy answer. This is the deepest problem with the idea. A black hole has an obvious recipe. A white hole does not. The equations of general relativity permit one, but the equations do not tell us how to build one. Nothing in the known universe seems to make white holes the way stars make black holes. There is no dying object we have found whose collapse turns inside out and begins pushing matter away. If white holes exist, they seem to have no natural factory. One idea, and perhaps the most striking one, is that white holes cannot be born at all. They can only have always existed. In this view, a white hole would be a leftover from the earliest moments of the universe, something baked into the initial conditions of the cosmos, rather than something formed later inside it. That would make white holes among the oldest objects imaginable, older than the first stars, older than the first atoms, old enough that their beginning would be tangled up with the beginning of everything. A competing view comes from certain models of quantum gravity, where a black hole slowly transforms into a white hole over vast stretches of time. In these models, the collapse never quite finishes. Instead, deep inside, quantum effects bounce the falling matter back outward. What began as a drain eventually becomes a fountain. The catch is that this bounce would take longer than the current age of the universe for any normal black hole. If it happens at all, we would not yet have seen it for the large black holes we know about. Only the tiniest primordial black holes, if they exist, might have bounced by now. That word, primordial, opens another door. Some researchers wonder whether the extreme conditions right after the Big Bang could have squeezed pockets of matter into miniature black holes, far smaller than any star. If those tiny objects then bounced into white holes on shorter timescales, the universe today could be quietly sprinkled with them. They would be among the rarest and strangest objects in the sky. Some might be no larger than an atom, yet contain the mass of a mountain. Nobody has ever confirmed such a thing exists. The extremes here are almost dizzying. A white hole, if it formed from the bounce of a primordial black hole, might be one of the smallest gravitational objects the universe can hold. A white hole, if it came from the initial conditions of the cosmos, might be one of the largest and oldest. The theory allows for both ends of the scale and offers little guidance about which, if either, is real. There is also the question of stability. Even if a white hole did form, many calculations suggest it would not last. Ordinary matter, falling toward it from outside, would pile up at its edge, and the gravity of that pile-up could crush the white hole back into an ordinary black hole almost immediately. In this picture, a white hole is the rarest kind of object because it is the shortest lived. It flickers into existence and vanishes before anyone can notice. Other researchers argue the opposite, saying that certain quantum effects could stabilize the fountain and let it glow for a very long time. So, the mystery of origin bends into a mystery of lifespan. If white holes are born easily but die quickly, we might never see one. If they are born rarely but live for eons, the sky should be dotted with them, and their absence becomes a puzzle in itself. Neither picture matches the observations we have. The evidence is quiet in every direction. Sit for a moment with that quiet. Somewhere in the equations there is a permission slip for these strange fountains. Somewhere in the universe, perhaps, that permission has been used. Or perhaps it has not. The extremes of the idea stretch from the first instant of the cosmos to the smallest quantum flicker, and the answer to where a white hole would truly come from remains one of the softest, most open questions in all of physics. We can only wonder gently as the stars keep turning above us. Somewhere in the mountains of data that pours in from our telescopes each night, there may already be a whisper of a white hole, or there may not be. That is the strange, quiet edge of this search. Astronomers are not looking for something loud or obvious. They are combing through faint flickers, brief flashes, and gentle anomalies, wondering if any of them might be the fingerprint of a fountain that cannot be entered. The candidates are small and shy. Most are not called white holes at all in the official records. They are logged as short bursts of light, or as odd little signals that do not quite fit the usual patterns. Some appear for less than a second. Some appear once and never return. In the deep archives, these fleeting events sit like pressed flowers, waiting for someone to look again. One of the most talked about examples came from a gamma-ray burst spotted many years ago, a brief flash of very high energy light from far across the sky. It behaved oddly. It did not seem to have the usual afterglow that follows the death of a massive star. It did not seem to fit the merger of two dense objects either. A small group of researchers wondered, quietly, whether it might be the signature of a white hole erupting. Others in the field pushed back, suggesting, instead, that it was simply a rare kind of stellar collapse we do not yet fully understand. The debate faded. The signal remained unexplained. That is the pattern again and again. A strange flicker appears. A few voices suggest an exotic origin. Most voices suggest something more ordinary, just poorly measured. And the flicker settles into the archive, neither confirmed nor denied. The trouble is that a white hole, if it exists at all, would probably not announce itself with a label. It would look like a burst of matter and light coming from a place where no star had been. It might resemble a young supernova, or a flaring quasar, or the tail end of some other violent event. Telling one from the other requires patience, careful measurement, and a bit of luck. The universe rarely hands over clean answers. Some researchers have tried to imagine what a truly small white hole might look like if loop quantum gravity is right, and some black holes slowly turn into white holes over immense stretches of time, and the smallest, oldest ones might be releasing their contents right now. The signal would be faint. It might appear as a soft glow in the radio sky, or as a gentle pop of high-energy particles arriving at Earth from no obvious source. Searches have been made. So far, nothing conclusive has turned up. The sky has not shown us anything but only a white hole can explain. There are gentler hints too in the cosmic ray record. Every so often, our detectors catch a particle arriving from space with an energy so high it is difficult to account for. Where did it come from? What accelerated it to such a speed? The usual suspects are exploding stars, active galactic centers, and the tangled magnetic fields of distant galaxies. A few thinkers have wondered, quietly, if a white hole somewhere might be flinging out matter at these energies. Most feel that ordinary sources are enough. The question has never been fully closed. Radio astronomers have their own small catalogue of curiosities. Fast radio bursts, tiny chirps of radio waves lasting only milliseconds, arrive from all across the sky. Their sources are still being sorted out. Most now seem to come from certain kinds of dense stars with powerful magnetic fields. A handful, though, remain hard to place. In the early years of the search, a few researchers floated the idea that some of these bursts might be the last exhalation of a black hole turning inside out into a white hole. The idea has not been ruled in or ruled out. It sits in the drawer of unlikely but not impossible ideas. What makes all of this beautiful, in a quiet way, is the texture of the search itself. Astronomers spend nights peering at spreadsheets of photon arrival times, plotting little peaks and troughs, comparing them to models of stellar death, of neutron collisions, of magnetic flares. Somewhere in that patient work, a white hole might already be hiding, misfiled under another name, or the archive may hold nothing of the kind, and the fountain may exist only in equations. For now, the best signals are ambiguous, and the ambiguity is itself the news. The sky has not shown us proof. It has not shown us absence either. It has only shown us patterns we do not yet fully understand, glowing softly in the deep quiet of the night. The story of how we came to imagine white holes is a slow one, unfolding across half a century of quiet mathematics, rather than any single moment of discovery. There was no sailor who spotted one on the horizon. No astronomer pointed a lens at the sky and cried out. The white hole was born on paper, in ink, in the margins of equations that seemed to be describing something else entirely. It begins with a young German soldier named Karl Schwarzschild, working out solutions to Einstein's field equations during the First World War. He was solving the geometry of space around a single, still, round mass. What he found was strange. His equations pointed to a place where space itself seemed to fold inward. He died shortly after sending his work to Einstein, never knowing what his solution would come to mean. For decades, most physicists treated the odd feature in his math as a quirk, not a real object. The word black hole would not enter common use until the 1960s, and tucked inside the same math, waiting patiently, was a second strange feature. When physicists began drawing careful maps of Schwarzschild's solution, they noticed something unsettling. The equations did not describe only a place where matter fell in. They also described a place where matter came out, a time-reversed twin, a region no one could enter, only leave. Two physicists helped make this picture clear in the late 1950s and early 1960s, Martin Kruskal in the United States and George Chekeres in Australia. Working independently, extended Schwarzschild's map into a fuller shape. Their combined work gave us what is now called the Kruskal-Chekeres diagram. It looks a little like a diamond divided into 4 regions. One region is our familiar universe. Another is the black hole interior. A third is a mirror universe, perhaps unreachable. And the fourth is the white hole. There it sat, staring back from the math, as valid as any of its neighbors. Kruskal had not set out to invent a new object. He was cleaning up an old solution, removing an illusion that had troubled physicists for years. The white hole was a byproduct, a ghost that appeared once the geometry was drawn properly. Many took it as a hint that the math was more generous than reality. The equations allowed something the universe might quietly refuse to build. Igor Novikov, a Soviet astrophysicist, took the idea more seriously. In the 1960s, he wondered whether these time-reversed regions might exist somewhere, and whether the newborn universe itself might contain leftover white holes from an earlier phase. Around the same time, other researchers began asking a harder question. If white holes could form, how long would they last? And here the picture darkened. The calculations suggested a very short life. A white hole sitting in our universe would face a constant rain of light and dust and stray particles falling toward it from outside. But nothing could actually reach its surface, because nothing can enter a white hole by definition. Instead, matter would pile up just outside, growing hotter and heavier. The resulting shell of trapped material would, in most models, choke the white hole almost as soon as it appeared. Some studies suggested it would collapse back into an ordinary black hole in a brief, violent flash. This is the strange arc of the theoretical white hole's biography, born from equations, recognized as a formal possibility, then argued by many of the same physicists who found it to be so fragile that it could not survive its own birth. A creature of ink and thought, blooming and vanishing in an instant, even in imagination. Yet the idea has never quite died. In the 1970s and beyond, researchers explored whether a very early white hole, one that emerged when the universe was young and empty, might have lived longer. With less matter around to smother it, its fountain might have kept flowing for a while. Others wondered whether the whole cosmos began as one enormous white hole opening. And in more recent decades, work in loop quantum gravity has revived the picture in yet another form, suggesting that ordinary black holes might slowly transform into white holes over spans of time so long that no telescope could yet catch the moment. So there was no single discovery, no plate developed in a darkroom that showed a fountain in the sky. There was only a long, careful reading of the equations, and a growing suspicion that the universe might contain a shape our instruments have not yet learned to see. Whether it truly does, or whether the math has simply offered us a possibility the cosmos never chose to use, remains one of the quiet, open questions. There is a puzzle at the heart of black hole physics that has troubled thinkers for decades. It is called the information paradox. When something falls into a black hole, a book, a star, a single photon of light, the details that make it unique seem to vanish from the outside universe. Quantum mechanics says this cannot happen. In its rules, information is never truly lost. It can be scrambled, hidden, spread across many particles, but it must, in principle, always be recoverable. Black holes seem to break this rule, and this is where the theoretical white hole quietly enters the conversation in a strange and surprising way. If a white hole is the time-reversed twin of a black hole, then it does the opposite of hiding. It reveals. It pours matter and light outward instead of pulling them in. Some thinkers have wondered whether the information swallowed by a black hole might not be destroyed at all. Instead, it might re-emerge, perhaps in the very distant future, through a white hole. In this picture, every black hole could be the entrance to a slow, patient fountain that eventually gives back what it took. The universe would keep its books balanced just across an enormous stretch of time. This idea is not accepted physics. It is one of several attempts to solve the paradox, and each attempt has its own critics. A competing view holds that the information leaks out gradually through the faint glow known as Hawking radiation. without any white hole needed at all. In that picture, the black hole slowly evaporates over unimaginable ages, and the details of what fell in are carried away in the subtle patterns of that dim light. Both ideas try to save the same rule. Both remain unproven. The question of which, if either is correct, is still very much open. There is something quietly counterintuitive here. A black hole feels like a place where things end. A white hole, in this speculative picture, would be a place where things begin again. The same object, seen forward in time, would be a devourer. Seen backward, or seen at the far end of its life, it would be a giver. Whether nature actually allows such a two-faced existence, no one knows. Loop quantum gravity, one of the more mathematical attempts to unite gravity with the quantum world, offers a further surprise. In some of its models, a black hole does not simply evaporate. Instead, deep inside, where the old equations predict a point of infinite density, the quantum rules take over and prevent that point from ever forming. Matter is squeezed, held, and then, after an enormous quiet interval, released. The black hole, in this picture, slowly transforms into a white hole. The transition would look sudden to an outside observer, though the inner process might take longer than the current age of the universe. This is a beautiful idea, and it is only an idea. Other researchers are not convinced. They point out that the calculations rely on assumptions that have never been tested, and that the models sometimes disagree with each other about how long the transformation would take, or whether it would happen at all. Some estimates put the timescale near the square of the black hole's mass in certain units, which, for a star-sized black hole, could be shorter than the age of the cosmos. Other estimates push the timescale so far into the future that no such event could have happened yet. The spread of predictions is itself a sign of how young this line of thinking still is. What makes all of this strange is the way it changes the meaning of the objects themselves. If black holes truly become white holes, then the darkest, most silent places in the universe would be, in the deep future, gentle sources of released matter and light. The graveyards would become nurseries. The one-way streets would reverse. The night sky, given enough time, might slowly fill with the faint returning breath of everything that had ever fallen inward. None of this has been observed. There is no signal, no clear fingerprint, no known event that requires this picture to be true. The information paradox remains unsolved, and the role white holes might play in solving it remains a matter of quiet debate among specialists. Some find the idea elegant. Some find it forced. Most agree it is worth thinking about, precisely because the alternative, that information really is destroyed, would break a rule that quantum mechanics has never before allowed to bend. So the surprise, if there is one, is not an answer. It is a question that keeps circling back. Perhaps what falls in must, in some strange way, come out. Perhaps the universe forgets nothing. Perhaps it only takes its time. The white hole question does not sit alone in a quiet corner of physics. It touches almost every other deep question we have about the universe. And that is part of why the debate around it stays so gentle, so slow, so patient. When physicists gather to talk about white holes, they are rarely just talking about white holes. They are talking about time, about gravity, about the beginning of everything, about what happens inside a black hole where no telescope can ever look. The white hole is a thread. Pull on it, and the whole fabric of modern physics shifts a little. Consider how it connects to the study of black holes themselves. For decades, researchers have tried to understand what happens at the center of a black hole, at the point where the equations of general relativity stop giving sensible answers. Some think the answer involves a bounce a moment when collapsing matter reaches a limit and turns around. If that bounce is real, then the object we call a black hole might, in the distant future, become a white hole. The two ideas are not rivals in that picture. They are the same object seen at different stages of its long, slow life. Other physicists find this unconvincing and prefer models where black holes simply evaporate through faint radiation, leaving nothing behind. The debate is quiet because no one can test either idea yet. The question also brushes against the study of the Big Bang. Cosmologists who model the earliest moments of the universe sometimes find their equations resembling the equations of a white hole, at least in certain limited ways. Matter and light poured outward from a hot, dense point. Nothing could enter that point from our side of time. The parallel is striking, and a small group of researchers has explored whether the Big Bang itself might be understood as the outward mouth of such an object. Most cosmologists remain unconvinced and prefer other frameworks, such as inflation, where the early universe expanded from a smooth quantum state. Both pictures leave gaps. Both continue to be studied side by side. Then there is the connection to thermodynamics, the branch of physics that describes heat, entropy, and the flow of time. Entropy is the measure of disorder, and in our universe it almost always grows. Ice melts, stars burn out, rooms get messy. A white hole, if it existed, would seem to run against this flow. It would take a highly ordered state and release it outward, which looks strange when compared to everything else we observe. Some physicists argue this alone rules them out. Others counter that the early universe itself was in a very low entropy state, and no one fully understands why. If we cannot explain that, they say, we cannot casually dismiss white holes on entropy grounds either. The question reaches further still, into the field known as quantum gravity, where the rules of the very small are stitched together with the rules of the very large. Different approaches to quantum gravity give different answers about whether white holes can exist. In one framework called loop quantum gravity, tiny grains of space itself prevent full collapse, and a black hole may eventually rebound into a white hole after an enormous span of time. In string theory, the picture looks different, with black holes described as complex arrangements of quantum threads. These frameworks are still being developed, and neither has produced a clear, testable prediction that could settle the matter. Even the study of information. What happens to the data carried by matter that falls into a black hole bends toward the white hole question. If information cannot truly be destroyed, then somehow it must come back out. Some researchers wonder whether a white hole phase, however brief or delayed, might be part of that return. Others believe information leaks out slowly through faint radiation and never needs a white hole at all. The disagreement is polite, unresolved, and ongoing. What makes this debate so gentle is that no one is angry. No one is certain enough to be angry. The evidence is thin. The mathematics allows more than one story. The universe, so far, has not spoken clearly on the matter, so physicists sit with the question the way a person sits with a puzzle box in low lamplight, turning it slowly, listening for the faint click of a hidden mechanism. They know that whichever way this question resolves, it will reshape our understanding of gravity, time, and the origin of everything. And they know that the answer, if it comes at all, may take generations. For now, the debate hums on quietly, patient as the stars themselves, waiting for a signal that may or may not arrive. Something quiet has been shifting in the way physicists think about white holes. The change did not arrive as a single discovery or a bright announcement. It arrived slowly, over decades, through small mathematical whispers from the strange world of quantum theory, and it is still arriving now, one soft revision at a time. For most of the 20th century, the white hole was treated as a curiosity of the equations, a ghost in the math, something the classical theory of gravity allowed on paper, but that the real universe seemed to reject. The picture was tidy. Black holes swallow. White holes, if they existed, would spit, and since no one had ever seen anything spit in that particular way, the idea drifted to the edges of physics. Then quantum ideas began to seep in, slowly, patiently, the way water finds the smallest cracks in stone. Once, physicists started asking, what happens when quantum rules meet the deep interior of a black hole? The sharp line between the two kinds of holes began to blur. One line of thinking comes from loop quantum gravity, a proposed theory that tries to describe space and time as woven from tiny threads. In this picture, space cannot be squeezed smaller than a certain size. It has the smallest possible grain, and if that is true, then the crushing center of a black hole, the point where old theory says everything ends, might not be a true end after all. The matter falling in would be squeezed down to that smallest grain, then gently pushed back outward. Over an enormous span of time, the collapsing star would slowly turn itself inside out. The black hole in this view becomes a white hole, not by breaking any rule, but by finishing a very long process. This is only one theory. Other physicists prefer a different picture, in which the interior stays hidden forever, and no such reversal ever occurs. In their view, whatever falls in stays lost to the outside, and any hint of a white hole phase is a mathematical illusion. The debate is not settled. The evidence, so far, is only in the equations. What has changed is the mood around the question. 50 years ago, white holes were almost embarrassing to mention. Today, serious researchers write serious papers about tiny primordial black holes, possibly reaching the end of their lives and flashing into brief white hole states. The idea has moved from the shadows into the quiet edges of respectable study. That shift is itself a slow transformation, a change in the culture of the field rather than in the universe itself. The universe, of course, keeps changing on its own. Black holes are not static. They very slowly leak a faint radiation, predicted by theory. Over spans of time so long they dwarf the current age of the cosmos, the smallest black holes would shrink and eventually vanish. What happens in that final moment is one of the deepest open puzzles in physics. Some models suggest a soft fade, others suggest a small, sudden pop, and a few suggest that the last instant looks briefly like a white hole opening its mouth and releasing whatever memory of matter it still holds. If that is true, then the sky is slowly, quietly filling with the possibility of such tiny events. Not now, not for a very long time, but in the deep future, as small black holes finish their long lives, the universe would be rehearsing, across billions upon billions of years, the very process the equations first hinted at. Even the way we search for these objects has been changing. Early searches looked for dramatic outbursts. Newer proposals look for softer, subtler signals. Faint flashes with a particular shape. Brief signatures that might match what a dying tiny black hole could produce as it turns. Nothing conclusive has been found. The searches continue, patient and quiet, sifting through data collected by telescopes that watch the sky in wavelengths our eyes cannot see. There is also a slower change happening inside the mathematics itself. Each generation of physicists refines the tools, sharpens the models, closes small gaps, opens new ones. A theory that once seemed forbidden becomes permitted under different assumptions. A theory that once seemed permitted turns out to depend on a step no one can quite justify. The picture keeps shifting, gently, like sand rearranging under a tide. None of this brings us to an answer. It only brings us closer to knowing what kind of answer we might one day accept. The white hole, if it exists at all, may not be a separate object at all. It may be a phase, a moment, a slow turning that any deep collapse eventually reaches, or it may remain a beautiful accident of the math. Tonight, the question is still open, and the whispers keep coming. If a white hole existed somewhere in the sky tonight, the first thing that would betray it would be the light. Not because we would see the object itself, but because we would see how space bends around it. The shape of space near any dense object curves like a soft valley, pulling the paths of passing photons into gentle arcs. Around a white hole, that valley would look almost identical to a black hole's from a great distance. And this quiet similarity is part of why we may have overlooked one already. Light near a strong gravitational well does something beautiful. It bends. A distant star behind such an object would not appear where we expect it. Its light would slide around the curve of space and arrive at our eyes from a slightly wrong angle. If several stars sat behind the object, their images would smear into thin arcs, sometimes forming a full ring of light around the invisible center. Astronomers call this ring an Einstein ring, and it appears wherever mass is dense enough to warp the sky behind it. A white hole, in theory, would produce the same rings. From far away, its gravity would pull on passing light in the same manner as a black hole of equal mass. This is one reason the two objects are so hard to tell apart at a glance. The equations that describe how space curves depend on mass and spin, not on which direction time flows inside the object. So, a photon skimming past a theoretical white hole would trace a path nearly identical to one skimming past a black hole. The lensing pattern in the sky would give little away. The difference, if any, would lie closer in. Near a black hole, light can fall inward and vanish behind the event horizon, that invisible boundary from which nothing returns. Near a white hole, the boundary works the other way. Light cannot enter it. Photons approaching from outside would be turned back or deflected, as if the region itself refused all incoming signals. A perfect white hole, in the classical picture, would be surrounded by a thin shell of light that could only leave, never arrive. Whether such a shell could hold together long enough to be seen remains an open question. The color of that light is another matter. Photons climbing out of a deep gravitational well lose energy as they rise. Their wavelengths stretch, and they slide toward the red end of the spectrum. This is called gravitational redshift, and it happens to all light escaping any strong source of gravity, including our own sun, in tiny amounts. Around a white hole, the light pouring outward would emerge from a region of extreme curvature. Some models suggest the light near the surface would be redshifted so severely that it would arrive as faint infrared or radio waves, glowing dimly rather than blazing. Other models suggest the opposite. If the matter erupting from a white hole carried enormous energy, its light might arrive blue-shifted from our perspective, bright and sharp and gone in an instant. There is a quieter possibility, one that physicists sometimes consider. A white hole might not glow steadily at all. It might release its light in a single silent flash, or in a slow trickle spread across billions of years. In-loop quantum gravity models, where black holes are proposed to slowly transform into white holes across immense timescales, the final release of light might be so gradual and so redshifted that it would look like nothing more than a faint hum in the background of the sky. We may already be bathed in such a hum without recognizing its source. The shape of space around a white hole would also affect shadows. A black hole casts a dark circle against any bright background behind it, a silhouette that telescopes have now imaged around distant galactic centers. A white hole, by contrast, might cast a bright disk. Light streaming outward from its surface would form a glowing patch surrounded by the ordinary darkness of empty space. Whether such a disk has ever been photographed and simply misidentified as an ordinary star or bright knot of gas is a question no one can fully answer. For now, light is our only messenger from the deep universe, and it carries whatever information the geometry of space allows it to carry. Around a theoretical white hole, that geometry would tell a strange, half-familiar story. Rings of lensed starlight, a brightness that leaks outward, but never inward, a color that shifts depending on the model you trust. The picture is coherent in the mathematics and blurry in the sky, and the mystery of what such light would truly look like remains, for tonight, unresolved. Space is often called silent, and in one way that is true. Sound waves need matter to move through, and the vast stretches between stars hold almost nothing. Yet, the universe is far from quiet. It hums and rings and shivers in ways we can measure, and if a black hole ever did turn into a white hole, that transformation might carry a signature we could almost hear. Consider what instruments have already caught in the Perseus galaxy cluster. A supermassive black hole sends pressure waves through the hot gas that surrounds it. Astronomers translated those waves into a note, a deep, steady tone, many octaves below anything a human ear can register. It is the lowest sound ever found in nature, and it has been ringing for millions of years. The black hole is singing, in a slow, patient way, into the gas around it. Now imagine the reverse. If a black hole, after countless ages, quietly flipped into its time-mirrored twin and began pouring matter back out, the gas around it would ring in a different way. Instead of being pushed by a slow drumbeat from a hidden center, it would be shoved outward by a sudden fountain. The pressure waves would still be there, but their pattern would change. Some researchers wonder whether such a shift, if it ever happened, might leave a faint acoustic fossil in the gas of a distant cluster. Others doubt any signal would survive long enough for us to notice. Gravitational waves offer another kind of sound. When two black holes spiral together and merge, they send ripples through the fabric of space itself. Detectors on Earth catch those ripples and convert them into short, rising chirps. Tiny audible whispers from events that happened billions of years ago. The chirp climbs in pitch, then ends in a soft ring as the new black hole settles down. It is a sound of things falling in, a white hole birth, if such a thing occurs, might sound like the chirp played backward. One idea from loop quantum gravity suggests that a black hole, over immense stretches of time, could slowly rebound into a white hole once quantum effects deep inside overcome the pull of gravity. If that rebound ever released gravitational waves, they would carry a very different fingerprint. Instead of a rising chirp ending in a ring, there might be a soft ring opening into a falling note, a spreading rather than a squeezing. No detector has ever caught such a pattern. Whether that means white holes do not exist, or simply that we have not listened long enough, remains an open question. There are other sounds the universe makes that touch on this puzzle. The cosmic microwave background, the faint afterglow of the young universe, has been translated into a soft hiss, like distant rain on a metal roof. Hidden inside that hiss are tiny variations that map the seeds of every galaxy. Some researchers have asked whether traces of a white hole event, perhaps even the Big Bang itself, if it was one, might be buried in that pattern. Others argue that the standard picture already fits the data well, and no extra ingredient is needed. The debate is quiet, technical, and unresolved. Even the solar wind, when its magnetic fluctuations are turned into audio, sounds like a low breathing whistle, the star exhaling into the dark. A black hole, feeding on gas, produces its own kind of exhale in the form of hot jets that scream in radio waves. Those jets, converted to sound, come across as static laced with pops and cracks. A white hole, in the models where it exists at all, would not feed. It would only give its acoustic character, if it had one, might be softer, more like a slow release of pressure than a violent roar. No one has ever recorded such a thing. It lives, for now, only in equations. There is something soothing about the idea that even a theoretical object might have a voice. The universe seems to insist on vibration wherever there is matter and energy to carry it. Stars ring like bells when they shake. Neutron stars glitch and spin and send out ticking pulses. Black holes hum in the gas that surrounds them. If white holes exist somewhere, in some quiet pocket of space, or in some deep future, they too would likely have a sound. We do not know what it would be. We do not know if anyone will ever hear it. The question of whether black holes can become white holes waits, patient and unanswered, in the low, steady drone of a universe that keeps on singing to itself in the dark. The mathematics of general relativity has a strange kind of beauty. It does not ask permission from our intuitions. It simply follows its own rules, drawing pictures of space and time that sometimes surprise even the people who study them for a living. And when those rules are followed all the way to their natural end, they suggest something remarkable. A black hole, drawn out in full on the page, seems to open onto more than just itself. It seems to connect to a mirror region, and beyond that mirror region, to another universe entirely. The picture that shows this most clearly is called the Kruskal-Sekeres diagram. It is a way of drawing the full geometry around an idealized, unchanging black hole. The diagram has 4 regions. One is the outside of the black hole, the region where we live and where distant stars burn quietly. Another is the interior, the place matter falls into and cannot leave. But the diagram does not stop there. It also contains a third region, a time-reversed twin of the black hole interior, which the equations call a white hole. And it contains a fourth region, another outside, another universe, separated from ours by the geometry itself. The math is elegant in the way a folded piece of paper is elegant. Take a flat sheet, fold it once, and the two ends meet across a valley. The valley is the bridge between them. In the diagram, that bridge is what physicists call an Einstein-Rosen bridge, a narrow throat of geometry linking our universe to the other. It exists on the page. Whether it exists anywhere else remains an open question. The ratios and rules that produce this picture are simple to state, if not simple to solve. The size of the throat depends on the mass of the object. Double the mass, double the radius of the event horizon. It is a clean linear relationship, the kind that mathematicians love. The curvature of space near the throat follows a smooth inverse cube law, falling off as you move outward, growing sharper as you move in. There are no messy corrections, no strange constants pulled from nowhere, just mass, distance, and the speed of light, arranged in the tidiest possible way. And yet from this tidy arrangement, comes the wildest suggestion in modern physics. If you took the diagram at face value, you would say that every black hole comes paired with a white hole in a separate universe, joined by a bridge of curved space. The math does not argue, it simply draws. Most physicists believe that the bridge, in any realistic setting, cannot be crossed. The geometry inside is not static. It stretches and pinches shut faster than anything. Even light could pass through. A traveler who tried to cross would find the throat closing around them before they reached the other side. The math permits the bridge to exist as a shape. It does not permit it to be used as a road. That, at least, is one interpretation. Others wonder whether more exotic ingredients, some form of matter with unusual properties, might hold the throat open long enough for something or someone to pass. No such matter has been observed. The question sits open. There is another elegance worth pausing on. The equations that produce this picture are time-symmetric. Run the clock forward, and you see a black hole. Run the clock backward, and you see a white hole. The math does not prefer one direction. It treats past and future as mirror twins, equally valid, equally real. What breaks the symmetry, as far as we can tell, is not the geometry, but the arrow of entropy, the tendency of disorder to grow. Some researchers wonder whether that arrow is fundamental, built into the fabric of reality, or whether it is a local accident, one that could point differently in a universe on the other side of a bridge. The distances involved, when the diagram is applied to a real black hole, are almost absurdly small. A stellar mass black hole has a throat only a few kilometers wide. A supermassive one, the kind at the center of a galaxy, might have a throat measured in the size of our solar system. These are not vast cosmic tunnels. They are compact, delicate, and, if the current picture holds, fleeting. Still, the shapes on the page keep their strange promise. Two universes joined by a bridge, a black hole feeding one, a white hole spilling into the other. Whether any of this describes something real or only something the equations happen to allow remains one of the quietest and most patient mysteries in modern physics. A white hole, if it exists at all, would be an object of astonishing fragility. It would sit balanced on a knife's edge, held together by conditions so precise that a single small change could unmake it. This is one reason many physicists doubt that such objects could survive in our universe long enough to be seen. The equations may permit them, but the world around them seems almost designed to tear them apart. Consider what a white hole must do just to exist. It has to push matter outward against the pull of its own gravity. It has to keep its horizon smooth and unbroken. It has to remain isolated from anything falling toward it, because anything that fell in would, in theory, destabilize the whole structure. The problem is that space is never truly empty, even in the deepest voids between galaxies. Thin gas drifts, faint light travels, and stray particles wander through. A white hole would be trying to expel matter into a place that already contains a little matter of its own. Some physicists have argued that this alone would be enough to ruin it. The infalling material, however small, would pile up near the horizon. As it piled up, it would gain energy. In some models, that energy would grow so quickly that it would form a shell of intense radiation around the white hole, a kind of blazing skin. This idea is sometimes called a firewall. The word simply describes a boundary of extreme energy, where soft, smooth space-time should have been. If a firewall formed, the gentle fountain of the white hole would be surrounded by a wall of fire made from the very matter it was trying to keep away. There are competing views on how serious this really is. One camp argues that the firewall is unavoidable, and that it converts any would-be white hole into something closer to an ordinary black hole, almost the moment it appears. Under this view, the universe simply does not tolerate outward-only objects. The tiniest disturbance folds them back into the familiar inward-pulling kind. Another camp argues that the firewall might be softer than it sounds, or that quantum effects could smooth it out. In that picture, a white hole could survive for a short while, glowing at its edges before eventually collapsing. The delicacy here is easier to feel by comparison. Think of how narrow the conditions are that let a planet hold on to life. A world needs a stable star, a steady orbit, a thin skin of air, a magnetic shield, liquid water resting between freezing and boiling, and a slow churn of heat from within. Move that world a little closer to its sun, and the oceans boil away. Move it a little farther, and they freeze, thin the air, and the surface bakes under raw starlight. Thicken it too much, and the ground crushes under its own sky. Habitability sits on a narrow ledge. A white hole, by many models, sits on a ledge even narrower than that. Its balance is not measured in degrees of temperature or kilometers of orbit. It is measured in the flow of a single particle. One stray atom, drifting the wrong way at the wrong moment, might be enough to change its nature. In this sense, the white hole is almost the opposite of a planet like ours. Earth is a small marvel of many things going right for a very long time. A white hole would be a small marvel that could only last for a very short time, if it managed to appear at all. This is why some researchers now describe white holes less as places and more as events, a brief flare, a sudden outward pulse, a moment when the geometry of space-time opens the wrong way before closing again. The question then shifts. Instead of asking whether white holes exist as long-lived objects, we might ask whether the universe contains many quiet, tiny openings that we simply never notice. The fragile balance would not prevent them entirely. It would only prevent them from lasting. None of this is settled. The firewall itself remains a debated idea, tied to unresolved questions about how quantum mechanics and gravity fit together. Some physicists think firewalls must exist for any horizon. Others think they cannot. The white hole sits in the middle of this argument, waiting patiently for a theory that can hold it steady. Whether the equations describe something real, or only something almost real, may depend on which side of that debate turns out to be closer to the truth. For now, the fountain and the firewall remain locked together in thought, each defining the other, each still waiting. Even after a century of watching the sky with better and better eyes, there are still signals from space that no one can fully explain. Some of them are quiet, some of them arrive as bright flashes lasting only a fraction of a second, and a few of them, if you allow your imagination to wander, look almost like the fingerprints a white hole might leave behind, if such a thing existed. This is not a claim. It is only a soft, open corner of astronomy where the unknown still lives. Take the highest energy cosmic rays. These are tiny particles, mostly protons, that slam into the upper atmosphere, carrying more energy than any machine on Earth can produce. One famous event, detected in the early 90s, hit with such force that scientists gave it a nickname and puzzled over it for decades. Where do these particles come from? What natural process can accelerate a single proton to such tremendous speeds? The usual suspects include exploding stars, the tangled magnetic fields near giant black holes, and the shock waves of colliding galaxies. Those explanations cover most of what we see, but not all of it. A small number of researchers have gently asked whether a sudden outburst from something like a white hole could, in theory, hurl matter outward with the kind of energy required. Others answer that we do not need such an exotic idea. Ordinary, if extreme, astrophysics can probably do the job once we understand it better. The disagreement is quiet and unresolved, and that is part of what makes the topic so interesting to sit with at night. Then there are the fast radio bursts. These are brief flashes of radio waves, lasting only a few thousandths of a second, arriving from galaxies far beyond our own. The first was noticed in archived data from an Australian telescope, and since then, hundreds more have been spotted. Some repeat, some appear only once and never return. Some seem to come from magnetars, which are neutron stars with unbelievably strong magnetic fields. That explanation fits many cases. It does not obviously fit all of them, because white holes, if they exist at all, would likely be short-lived and explosive. A few papers over the years have wondered aloud whether a white hole popping into visible existence might announce itself as exactly this kind of brief, powerful burst. The math is speculative. The predicted signatures do not perfectly match what has been observed, but they do not perfectly rule it out either. Most astronomers treat the idea as a curiosity rather than a leading theory. Still, the door has not been closed. There are other loose threads. Certain gamma-ray bursts, those extraordinary flashes of high-energy light from distant space, remain only partly understood. The long ones seem to come from collapsing massive stars. The short ones seem to come from neutron stars merging. Yet a small residue of events fits neither pattern cleanly. What produced them? No one is fully sure. Some are likely rare variations of known phenomena we have not yet observed enough of. A few researchers have wondered, with careful language, whether the sky is still hiding a category of event we have not learned to name. There is also the deeper mystery of the arrow of time itself. We watch the universe expand. We watch stars burn out and matter cool. Entropy, the measure of disorder, only seems to grow. A white hole would be a small local pocket where that arrow briefly bent the other way. If such pockets exist, they might be extraordinarily rare, or extraordinarily brief, or hidden inside events we already see and simply misinterpret. We do not know. The instruments needed to tell the difference may not exist yet. What ties all of these unsolved threads together is not any single piece of evidence. It is the shape of the gap in our knowledge. The universe still hands us signals we cannot fully account for. Most of them will one day be explained by ordinary physics, pushed to extraordinary conditions. That is the way science usually resolves its mysteries. But the possibility that one or two of these strange signals might carry information about something truly time-reversed, something that pours out instead of drawing in, cannot yet be entirely dismissed. So the sky above us is full of small puzzles, bright particles that should not exist, radio flashes with no obvious sender, gamma bursts that do not fit their families. Somewhere in that collection of loose ends, the fingerprint of a white hole may or may not be waiting. If it is there, we have not yet learned to recognize it. If it is not, we will still, in the searching, learn a great deal about the real workings of the cosmos. Either outcome is worth staying curious about, quietly, from a comfortable distance. Imagine stepping outside a very long time from now, far past our own lives, past the age of our sun, past the slow reddening of the sky, as our star swells into its final shape. Picture the Earth long changed, its continents drifted into new shapes, its oceans reshaped by tides. No one is left to measure. And now picture a night sky above that distant Earth, or above some other quiet world orbiting a younger star. What might it look like if white holes, the theoretical opposite of black holes, were real and scattered through the cosmos. One idea, offered by some who study loop quantum gravity, is that black holes slowly turn into white holes over immense stretches of time. In that picture, the black holes forming today are not endings at all. They are cocoons. Inside them, matter pauses, waits, and eventually rebounds outward through a kind of quantum bounce. If that is true, then the far future sky might slowly fill with soft, ghostly eruptions where black holes once sat in silence. A distant world's astronomers, if any exist, might see the darkness gently blooming. But other researchers push back on this dreamy picture. They point out that a black hole's hawking radiation, the slow trickle of energy leaking from its edge, could carry away almost all of its mass long before any bounce could happen. In that competing view, black holes fade into faint whispers of light and never flip into fountains at all. The two ideas cannot both be right, and with no white holes seen so far, we simply do not know which future is waiting. Still, it is soothing to picture a sky billions of years from now, where here and there a tiny point of light suddenly appears where nothing was before. Not a supernova, not a flare, but something softer. A brief glow, warm and orange, that fades as quickly as it came. If loop quantum gravity's gentler version is correct, these little pops might be the last breaths of black holes that formed in our own era, releasing whatever they once swallowed back into the open cosmos. On truly long time scales, the numbers grow strange. A stellar black hole, if it does flip into a white hole in the way some models suggest, might take longer than the current age of the universe to do so. Maybe far longer, maybe so long that our present moment is only the earliest chapter of the story. The far future sky might belong to observers who see what we cannot, the slow completion of a process we can only sketch in equations. There is another possibility, quieter and stranger. Perhaps the universe as a whole is drifting toward a state where matter grows sparse, stars burn out, and the great structures of galaxies dissolve into thin, cold gas. In that far future, sometimes called the era of degenerate remnants, the sky would be nearly black. Against that blackness, even a single white hole eruption might shine like a lantern in an empty hall. If such events happen at all, they would be easier to notice in a universe that has grown quiet than in the busy one we know now. Some thinkers wonder whether the whole cycle might repeat. If the Big Bang itself carried the fingerprint of a white hole, as one speculative idea suggests, then perhaps every so often, in some corner of a much larger reality, a new fountain opens and a new cosmos unfolds. Others find this notion untestable and prefer to stay closer to the equations we can check. The debate is old and unhurried, and it does not seem likely to resolve soon. For now, the sky above us shows no confirmed white hole. No gentle eruption has been traced back to one of these theoretical fountains. The searches continue, patient and slow. In 1,000,000 years, our instruments will be unrecognizable. In 1,000,000,000, our descendants, if we have any, may look at a different sky through different eyes. They may have answers we cannot even frame tonight, and it is worth sitting with that thought as the room grows still. The universe is always becoming something new. Stars are forming even now in clouds of dust we will never see up close. Old stars are collapsing into dense, quiet remnants somewhere. Perhaps the first faint signal of a bouncing black hole is already on its way to us, traveling across distances so vast that it will not arrive for ages. Or perhaps not. Perhaps the equations describe a beautiful possibility that nature simply chose not to use. The future sky keeps its secret, calm and patient, waiting for a listener who has the time. Step back with me now, all the way back, until the whole of our search sits small in the frame. For more than a century, since the equations of general relativity first hinted at these strange fountains of matter, we have looked. We have swept the sky with radio dishes wider than city blocks. We have tuned instruments to catch bursts of light, lasting fractions of a second. We have listened for tremors in the fabric of space itself. And in all that looking, in all that patient listening, we have never found a single object we can point to and say, with certainty, that is a white hole. The silence is strange. It is not the silence of an empty forest, where you know the trees are there, but the birds have gone quiet. It is the silence of a room, where you are not sure if anything was ever inside it at all. The equations promise the room exists. The mathematics opens the door and holds it open. But when we step through, we find no footprint, no warmth, no evidence that anything has ever passed the other way. Some researchers take this silence as an answer in itself. If white holes were common, they argue, we would see them. Their fountains of light would decorate the sky like rare and beautiful weeds. Since we do not see them, perhaps nature has some rule, still hidden from us, that quietly forbids them. Others hold a softer view. Maybe white holes are rare, or short-lived, or so tiny that they slip beneath every net we have cast. Maybe every fast radio burst, every unexplained flash, is a candidate we have not yet learned to read. The question sits open, patient, unbothered by our impatience, and yet, when you widen the view further, something gentle happens, whether or not white holes exist. The search for them has led us into a deeper understanding of how everything fits together. The same equations that suggest these fountains also describe the bending of starlight, the slow drift of galaxies, the tick of time near a massive body. To ask about white holes is to ask about the shape of the cosmos itself. It is to trace with a fingertip the outline of the rules that hold everything in place. Those rules made us. The calcium settled in your bones, quiet as chalk, was forged in the heart of a dying star long before the earth cooled. The iron warming your blood came from the same slow furnaces. The oxygen you breathe tonight passed through generations of suns before it found its way into the air of a small blue world. When you wonder about a white hole, you are wondering with atoms that were once part of something enormous. The universe is asking itself questions through you. That is perhaps the strangest gift of a mystery like this one. It reminds us that we are not separate from the thing we are studying. We are not tourists peering over a fence at the cosmos. We are made of it. The same laws that permit, or perhaps forbid, a fountain of matter in some distant corner also permit the soft rise and fall of your breathing right now. The arrow of time that points forward for a black hole and might point backward for its mirror twin is the same arrow carrying you gently toward morning. So the silence of the search is not really empty. It is full of everything we have learned along the way. It is full of the maps we have drawn, the models we have refined, the wrong guesses we have set aside, the right questions we have finally learned how to ask. Even a search that finds nothing changes the searcher. We know the sky better now than any generation before us. We know what is not there almost as well as we know what is. And somewhere, perhaps, the answer is waiting. Perhaps it will arrive in a signal too faint to have registered yet, a glow at the edge of a future telescope, a pattern buried in data we have already collected but not yet understood. Perhaps it will arrive as a proof, written on a whiteboard by someone not yet born, showing why such objects cannot fall. Perhaps it will never arrive at all, and the mystery will simply remain, kept safe by the mathematics that first suggested it. Either way, The wandering itself is a small act of belonging. To lie here in the warm dark and think about a fountain of light we may never see is to be part of the long, quiet conversation the universe has been having with itself since the first atom cooled. There is no hurry. The stars will keep their secrets a little longer. And so we come to the quiet end of our long wandering. The white hole, if it exists at all, has kept its silence through every page of tonight's story. We have followed it. Through the equations, through the diagrams, through the soft speculation of physicists who cannot quite let the idea go. And still, at the close, we hold the same open question we began with. Somewhere in the mathematics of our universe, there is room for a fountain of light and matter, a mirror to the drains we call black holes. Whether nature ever built one, we do not know. Perhaps that is enough for one night. Not every question needs an answer to be beautiful. Some questions are lovely precisely because they remain open, like a door left ajar in a warm house, letting in a thin line of starlight. Picture for a moment a small blue world spinning quietly in the dark. Its oceans move in slow, patient tides. Clouds drift across its face in soft white ribbons. On the night side, faint lights glimmer where sleeping cities rest. Around this world, the moon turns its old and cratered face, catching the sun that neither of them can see just now. And, beyond the moon, the deep black of space stretches on, sprinkled with the light of stars that have been shining for longer than anyone can hold in their mind. Somewhere out there, in that soft darkness, the questions we asked tonight are still waiting. A black hole is still bending light around itself, silent and slow. A galaxy is still turning, one full rotation every few 100 million years, unhurried by anything we do. A cosmic ray is still crossing empty space, carrying its small, strange message from a source we have not yet identified. And a white hole, if such a thing exists, is either resting somewhere in its impossible quiet, or is waiting to be understood in a way we have not yet imagined. The universe does not seem to be in any hurry to tell us. It moves on its own long clock. Stars form over millions of years, planets cool over billions. Light from the edge of the visible universe has been traveling toward us since long before the Earth was here to receive it. Against that steady, patient rhythm, our questions are small and brief, and yet the universe seems to make room for them anyway. It lets us look, it lets us wonder, it lets us build our equations and our telescopes and our long, dark nights of thinking. Maybe one day some quiet observation will settle the question of the white hole. A strange burst of light with no source, a gentle glow that matches the mathematics too well to be coincidence. A signal from the long, slow end of a black hole's life, converting itself into something new. Or maybe the answer will be that no such object was ever needed, that the universe found other ways to balance its books, and the white hole will remain a beautiful ghost in the margins of our textbooks. Either ending would be worthy. Either ending would be a kind of gift. For now, though, the sky above you is doing what it has always done. It is holding its old, patient light. It is turning slowly as the earth turns beneath it. It is offering the same quiet mystery it offered to every person who has ever looked up and wondered where all of this came from, and where it might be going, and whether anything ever comes back the other way. You are small, and the universe is vast, and that is not a lonely thought tonight. It is a gentle one. You are held inside something enormous and slow and unfinished. The questions are not urgent. The answers will come, or they will not. And either way, the stars will keep on with their soft, ancient burning. There is nothing you need to solve before morning. There is nothing you need to hold on to. Let the white hole rest in its equations. Let the black hole keep its silent watch. Let the galaxies turn at their unhurried pace. Let the ocean of space carry its light from one shore of time to another. And let your breath grow slow and easy as you drift toward sleep. The mystery will still be here tomorrow. So will the wonder. So gently will you. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.